the thing you can do. Welcome. So we're going to talk about superposition and standing waves. What we're going to do is basically say, when two or more waves move in the same linear medium, linear not meaning a string, but meaning that 2 and 2 make 4. That's a linear medium. You know, they add up according to arithmetic. When two or more waves occupy a linear medium, then, let me move this out of the way. Then, let me go back. Then, when two or more waves occupy a linear medium, the net displacement of the medium, that is the resultant wave, at any point equals the algebraic sum of all the displacements caused by the individual waves. Bear with me 1 second.
Why did you add the 5 to 1 and not the other?
Let me get to that one. So we just add these. If it's a crest, it adds to a crest. If it's a trough, it adds to a trough. You know, it just adds linearly. But we've got to take both of them into account. So consider two waves that have the same frequency, same wavelength, same amplitude, and are traveling in a positive x direction. So they're both traveling in that direction, but they're kind of out of phase with each other. Well, this would be, it's a sine wave, A sine kx minus omega t. We did this before, didn't we? And what we said was, if you don't start off at the appropriate time, then we're going to account for that with a phase angle, which is what that is. So it doesn't have to be 90 degrees. In this case, it's not 90 degrees. It's that little bit that you're out. In fact, it's from there to there. It's that much. And if you think about this being something like, that's half a wavelength. So this would be more like 210 degrees or 360 minus 210 degrees. It's that bit. It can be any little bit you like. And we just add it in, so we end up with these two mathematical expressions. Now, I don't know about you, but I find adding that to that, giving me that, and adding that to that, giving me that, I get this really easily. It's intuitively obvious to me that this wave added to that wave gives me a lower amplitude wave, just by eyeballing it. But for some people, they need to do the math, so we say, well, y is equal to y1 plus y2, so let's add these two guys together. We get that, and then we've got to remember some trig function, I guess. How many people remember this? Not me either. So you get that, and then you've got to remember that A in this case is kx minus omega t, and B, of course, is kx minus omega t plus phi. And you add it together, and we end up with this answer. And as always with these things, we ask ourselves, what's it kind of saying? And what it's kind of saying is that we're going to get a peak height. This is determining my peak height, and it's going to be somewhat reduced. And this is my position. But if I was to change my omega, which is the thing I can change, my time, which is the thing I want to change, or maybe pick a time and change my x, then I would see wave like that. And if you've got time to kill, you might just run it through a calculator, but that's what happens. The key thing is, it mathematically justifies the superposition of waves. You add the two waves together and you get the overall result. Let's take the two extremes. You don't need to know those equations. You don't need to memorize them. I'd like you, if I throw one at you, I'd like you to know that omega is angular frequency in context. I'd like you to know what's going on with that. I'd like you to know the equation exists, so if later on you need detail, you can look it up. Let's take the two extremes. So in one extreme, I have one wave that looks like this, and it's going to superpose with a wave that looks like that. If I put them one behind the other, we see that they're in phase with each other, and so I add them up and it gets twice the amplitude. Same frequency, twice the amplitude. If I do this bit where one wave looks like that, but now this thing looks like that, and I put them together and I see where one is a crest, the other one's a trough, and where one's 0, the other one's 0, and so on, I get 0. So this is called destructive interference. And this is called constructive interference. So destructive interference and constructive interference. And they occurred because the two waves arrived in phase in this case, and the two waves arrived anti-phase. The crest arrived with a trough in that case. So a bit of language there, in phase and anti-phase. If I was to take a room and put two speakers in there, and those speakers were to hum at a constant frequency, and I walked around, I would find that I would get loud regions and dull regions. Effectively, I'd have silent bits and non-silent bits. Well, with vibration off the walls and stuff, it's not as obvious as that. And if you have complicated sound coming out of the speakers, like with your stereo system, you're not got the same thing occurring at all. You're not got the same frequency coming out of each speaker. So you're not going to see this effect. But if I could get my speakers to hum, I could move my head around and I could find, maybe not perfect silence, but quiet bits and loud bits. I can visualize the same thing really well using ripples on water. So imagine I have a bath and I have two little plungers which cause ripples. And the wave travels out, and it travels out relatively slowly because it's a ripple. And so here are the waves. I did a blue wave meaning a crest. I did a green bit meaning a trough. I did a blue bit meaning a crest, a green bit meaning a trough. Blue bit meaning a crest, green bit meaning a trough, etc. What this tells me is, because I get the crest here and the crest there, these speakers are in phase, aren't they? They're giving the compression or the crest and then the trough and then the crest and the trough. I'll go language backwards and forwards between crests and troughs and compressions and rarefactions because they can visualize the same thing. Sometimes I visualize the water ripples and sometimes I visualize the sound. And we notice there are these points where at this point here, a crest from one wave, from one speaker, or a compression, corresponded to a compression or the crest from the other speaker. Yeah? Constructive interference. And here, I didn't draw this one, but it would have been here. That would be constructive interference. There'd be another wave going like that. And that's constructive interference. And that's constructive interference. And there'd be a constructive interference there. So if I have the trough with the trough, giving me a really deep trough, that's constructive interference. Constructive interference. Constructive interference. Constructive interference. So you can see actually there's this channel of constructive interference that goes out from these things. If you were on a lake with these things rippling and you were anywhere on that line with your boat, you would feel the ripples really strongly because of this constructive interference. If you were in a room, you would hear the sound really loudly because of the constructive interference. If I do the same experiments, the same diagram, but here I'm looking for places where a crest or a compression corresponds to a trough or a rarefraction. So I'm looking for a place like that, or a place like that, place like that, place like that. And we see that there's avenues of destructive interference. And if you were anywhere on that line, you would feel very little ripple, or you'd hear very little sound. And these two are interspersed, so you get, compression, you get constructive interference, then a destructive interference, then a constructive interference, and so on. Okay. So if I picture a point, let's say I picture that point there, this is what my wave experience would be. And if I took the point, say, there, that is what my wave experience would be. Okay. Two speakers are in phase. That means they're both pushing and pulling at the same time. A listener stands equal distance from each speaker. What will she hear? Would she hear silence because of destructive interference, or loudness because of constructive, or silence because of constructive, or loudness because of destructive? If we have a speaker and a speaker, same medium, same type of wave, same speed, same distance traveled in a given time, a crest will arrive with a crest, or a trough will arrive with a trough. I'm going to get constructive interference, and it's going to be loud. So I would get loudness because of constructive interference. Yes?
Is there any way there can be silence?
Yes. If I was at a different, two ways. If I made this so that they were anti-phase.
No, let's say that they are in phase.
But let me, so if they were anti-phase, that point would be silence. But if they're in phase, if I am over to the side, I would hear silence. And we're going to do the math of the 2 points, yeah. I'm going to put this on pause. I've got to be careful. So we're back. And this is a video I want to show you, which is basically two, call them dippers, two little sources of vibration on a, in fact, let me see if I can find the sound as well. Sometimes this does not work, we'll see. On a ripple tank. Probably not going to work because there's like 5 places you can turn off the sound in these things.
In this film, we're concerned the interference patterns of ripples made on the surface of water. The ripples are produced in a ripple tank by 2 dippers which vibrate on the surface. Light passing through the water is reflected from a mirror through a lens to form an image of ripples on a screen. We've obtained this true image by the Schlieren technique of inserting a stop in the light path. The 2 small dippers vibrate on the surface of the water. Each dipper produces its own pattern of ripples, and the 2 sets of patterns overlap. In step, they produce a pattern like this. Out of step, they're vibrating in antiphase and produce a different pattern.
Notice where the
If we
avenues are.
study these patterns more closely, the images formed by the ripples have been slowed to 1/24th of their actual speed by stroboscopic means.
Notice this. This is in phase, and you're getting constructive interference down the middle, and you're getting destructive interference where you get these bits. Now, why is it that the destructive interference looks really narrow and the constructive interference looks really wide? I can't tell you. I don't have a good answer for that. But this is constructive interference with destructive interference in between, constructive interference with destructive interference. And it's symmetrical. So
2 sources appear vibrating in phase, producing crests and troughs in step with one another. The result is an interference pattern. Along these lines, the waves from the 2 sources always arrive out of step and neutralize each other, producing interference fringes of minimum wave motion. Minimum wave motion, maximum wave motion. Now the 2 sources are vibrating in phase about 5 wavelengths apart. When the dippers are moved closer together, the interference fringes spread out. When one of the dippers is moved...
So, let's go back just a little bit because I want to... I'm sorry. So what they've done here is they're bringing the 2 sources of energy closer together, and it's ironic, but the pattern spreads out.
Together, the interference fringes spread out. When one of the dippers is moved, these effects
really
are clearly
messes it up.
demonstrated, As the sources come closer together, the fringes are widely separated.
I'm going to stop that there because he goes on and does some other stuff that I'm not so interested in at this point. This kind of nudges me a bit. There's some videos that I have traditionally used that I've not transferred over to the new system that I'll try and be conscientious over this next few days and try and get some across. I'll probably do another page with a whole bunch of videos on for that, or links. But so you can see that this is a real thing. It's not just a mathematical thing. It's a real thing. I've got to start again from the beginning, and we've got to go to there. So here we are. So, okay, let's try and do a bit of math on this. And for that, this is my suggestion is you're going to look at the path difference and look at the phase difference. Let's start off with these guys in phase. So that guy is in phase with that guy. So what determines whether I get, at any instant in time, am I getting a crest or a trough? Well, I can divide this distance up into wavelengths. And I can say, well, I'm a certain distance away, so there's a certain time delay, so I'm getting a crest. And I can say, well, I'm a different distance away, so there's a different time delay, and now I'm getting another crest. It's not the same crest, it's another crest. But I don't care. Two crests together give me constructive interference. Or I can say, well, I'm a certain distance away, certain time away, I'm getting a crest. I'm a different distance away from the other speaker, a different time delay, I'm getting a trough. I don't care which trough it is, I'm just getting a crest with a trough, so there's destructive interference. So the trick is the distance is away, what we call the path difference. So what we say is, suppose we have two sources of wave that are in phase. Let us assume that the waves from each source interfere at point P. The path length from source S1 is R1. The path length from source S2 is R2. At one extreme, if the difference in path length between R1 and R2 is an even number of lambda over 2s, what does that mean? That means 0 lambdas, or 2, which is 1 lambda, or 4 over 2, which is 2 lambda, or 6 over 2. Why not just call it a whole number of wavelengths? Because we're going to contrast it with the destructive interference. So if you're an even number of half wavelengths, then you will get constructive interference. Because if the path difference is 1 wavelength, then the crest from one arrives when the crest from the other arrives. If you're 2 whole wavelengths away, the crest from one arrives when the crest from the other one's arriving. They're going to be in phase. Because I don't care which crest it is, I just care about the fact that it is a crest. But if I am an odd number of lambda over 2s, then when this crest arrives, by definition, I'm half a wavelength away from the crest for the other speaker, so that's going to be a trough. So I get destructive interference. If you like, kind of picture it like, it's hard to draw, but imagine it's like that and a crest arrived. And then down here, because I'm not as far away, I'm going to have a tough time drawing this, but yeah, a crest arrived with a trough. What's that difference in path difference? That would be lambda over 2, or 3 lambda over 2, or 5 lambda over 2, or 7 lambda over 2. I don't care. It's going to be an odd number of half wavelengths. So even number of half wavelengths, you get constructive. Odd number of half wavelengths, you get destructive. Does that make sense? Now, it turns out that sometimes we prefer to talk in terms of radians rather than wavelengths. Remember, 1 lambda equals 2 pi radians. So this would be not an even number of half wavelengths, it would be an even number of pi radians. because of half a wavelength. If one wavelength is 2 pi, half a wavelength is 1 pi. And this would be an odd number of pi radians. So I can characterize my path difference in terms of meters. It's 3 meters different. I can characterize it in terms of wavelengths. Take your number of meters and divide it by the wavelength. Or I can characterize it in terms of phase angles. Take your distance, divide it by your wavelength to get the number of waves. Multiply your number of waves by 2 pi. And you can look at the answer and say, is it constructive or is it destructive? Okay. There's an equation for this phase difference. And what does it say? It says, get your path difference in meters and then convert it into the number of wavelengths by dividing it by pi, and then convert it into a number of radians by multiplying it by 2 pi. Isn't that what we just said? So you can learn the equation or you can just follow the logic of it. Question?
Yeah, so you said the lambda is 2 pi.
I didn't say, no, I said lambda, one wavelength equals 2 pi radians. Yeah. Yep. So.
Okay. I was trying to see something to cancel that 2 pi, but I don't think there is.
No. So, let's consider a question. Consider the interference of 2 sound waves, 2 sound sources that are in phase. So don't need to worry about the sound sources. The distance R1 is 2.8. R2 is 2.2. The wavelength of sound is 0.4 meters. Show the phase difference at point P is 3 pi radians. So we're going to say, well, let's have a look. My path difference is equal to 2.8 minus 2.2, which equals 0.6 meters. That's my path difference in meters. My path difference in lambdas is going to equal 0.6 over 0.4, which equals 1.5 wavelengths. And then my path difference in radians is equal to 1.5 lambda. So that's the units. The units is lambda. It's not a function. It's not a variable. It's the units. Like that's meters. That's number of wavelengths. Maybe I put down number of wavelengths to kind of like show it's not just something to be substituted in for, which is what I was about to do. So this is 1.5, and each wavelength is worth 2 pi radians. So that would be 3 pi radians. See where that comes from? Get the path difference in terms of distance, get the path difference in terms of expressed as a number of wavelengths, multiply the number of wavelengths by 2.5. Cool? Yeah, okay. So next, this is the bit where I'm just telling you, look, we don't have to talk in terms of wavelengths, we can talk in terms of the phase angle. And so one wavelength is 2 pi radians, which by the way is 360 degrees, and half a wavelength is 1 pi radians, which is 180 degrees, and quarter of a wavelength is half pi radians, which is 90 degrees. And we use both degrees and radians to talk about this. Agreed? Yeah. Let's say that our source is not in phase. If the wave sources are not in phase, we must consider the phase difference in addition to the path difference. Because if I'm a quarter of a wavelength ahead, I've got to take that into account. If one speaker is a quarter of a wavelength ahead of the other, it's going to change things. So if the total effect is an even number of half wavelengths, so this is even, lambda over 2 or even pi, I get constructive. If it's an odd lambda over 2 or odd pi, then we're going to get destructive. But we've not just got the path difference effect. We have the phase difference effect because of the speakers. And we've got to take that into account. Okay, so let's do an example of that. Consider the interference of two sound waves that are sources that are out of phase by pi radians. When one of them is pushing, what's the other one doing? Agreed? If they're no phase difference, or if the phase difference is, so let's do this, 2 pi, or if the phase difference is 4 pi, it's the same. But if it's 1 pi difference, I'm half a wavelength behind. If it's, there's the top one going push, pull, push, pull, push, pull. If this is half a wavelength behind, if that is half a wavelength behind, then it's there. So now this one's going like that. So when one of them is pushing, the other one's pulling. That's half a wavelength. It's worthwhile playing with these things just to change it from a math problem to a visualization thing. Okay, so we know this phase difference is pi radians. The distance is 2.9. So this is 2.9. Oh, sorry, I did that. 2.9. And this is 2.5 meters. Show that the phase difference at point P is 3 radians. So let's have a look at this. My phase difference at P is equal to my phase effect plus path difference effect. I know my phase effect is pi radians. It tells me that. Plus. Then my path difference effect. Well, let's have a look. I'm going to get my path difference, which is 2.9 minus 2.5. That's my path difference in meters. Let's make it a path difference in wavelengths divided by my wavelength, which is 0.4 meters. That's my path difference in terms of number of wavelengths multiplied by 2 pi. That's my path difference effect expressed as a phase angle. So this is pi plus 0.4 over 0.4 is 1 pi plus 2 pi, which equals 3 pi radians. Yep. That's the skill. That's what I want you to know how to do that. Okay. Standing waves. So imagine that we have a piece of string. There's a good example. Piece of string. And the energy is going to the left and the energy is going to the right. Because it's got, why should energy only go one direction? We're bouncing it. So, well, if I have a piece of string and it goes on forever and I flick it, the energy only goes in one direction. But if I have an end and the energy bounces back, I have energy going in both directions. You get standing waves when the wave is trapped inside some limits. Well, I know the expression for a wave that's going to the right, and I know the expression for a wave that's going to the left, and because it's the same wave that's bouncing back on itself, the amplitude will be the same, and it's the same frequency, so omega will be the same, and it's the same angular frequency, so the k will be the same. the angular wave number, so k will be the same. So it's going to be the same equation. It's just going to have negative if it's going in a positive direction and positive when it's going into a negative direction. And so it's a linear medium, so we can do superposition and add these two waves together, and we get a sine kx minus omega t plus a sine kx plus omega t. And if I remember my trig function, then I get this. So if we look at this, we get twice the amplitude at the maximum, modified by this. That's what sines do. Sines say, well, it's as big as it could be, but it goes to 0 as well. So this is the actual maximum value, and it's 2 times what it originally was. It's still modified by some sine function. And then we have a time. So this is giving me the shape of it because it's in terms of x, and this is giving me the time variance of it because it's in terms of t. And if I were to plot that out, I would get what is a standing wave. And the standing wave is a wave. It's a bit of a misnomer. It's a wave. If I look at one of these lobes, at one instant it's like that, and then 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 it's like that. It is moving tremendously. It's just bouncing backwards and forwards. At some points, this point never vibrates, and that point never vibrates. So we can divide this up into what's called an antinode and a node. The nodes are the bits where there's no movement. On a guitar string, the nodes are the bits where you can put your finger and the note doesn't change. It's kind of like the nodes on a, well, you can the nodes are the standing bits. You can get them in guitar strings, you can get them in an organ pipe. A standing wave is an oscillation pattern. It is oscillating with a stationary outline. So there's the outline. It looks like that. The result of superposition of two identical waves traveling in opposite directions. Okay. So we say a standing wave is an oscillation pattern with stationary outline results from superposition of two waves, and there's the expression for it. And we can identify the nodes, and we can identify the antinodes, and the nodes are where this guy is 0, because if you multiply that amplitude by 0, you get nothing. And the antinodes are where this guy is equal to 1, and so we can play around with it and get some expressions. X is equal to 2 lambda over 4 plus 4 lambda over 4 plus 6 and 6 lambda over 4 and 8 lambda over 4 and the antinodes. And I don't know about you, but it's like I don't care so much about that. This is what I want you to visualize, which is this. There's a node. There's a node. This is allowed. This is a possible solution to this wave equation, because it has a node at each end, and you've got to have a node at each end of the guitar string. This is a node. That's a node. This is a different solution, but it's allowed. There's a node in the middle. There's no rule says you can't have a node in the middle. This is not allowed. I have a node here and an antinode there. That cannot occur. The next allowed one, that's allowed. I have a node at one end, node at the other. I have 2 nodes in the middle. The next one, let's see if I can do this. I might have mixed up there. Node, 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 node. Yeah, no, that's the next one. And then that's probably the easiest way to do it. That's the next one. These are harmonics. These are, when you pluck a guitar string, the reason why it sounds interesting is because you're not hearing just one note. You're hearing a family of notes, but they are harmonically related. they have frequencies that go together, and that's because they're solving the same limit solution to the mathematical problem. It turns out their frequencies are mathematically related. Second harmonic is twice the first harmonic. 19th harmonic is 19 times the frequency of the first harmonic. They're all ratios of each other. And that's the way they have to be, and that sounds great. If you want to make an alarm, have a whole bunch of frequencies that don't have relationships to each other. So the best alarms have frequencies that are prime numbers. You know, they hate it. It sounds awful. And there's actually research where they make better alarms, things that really get you to jump out of your seat. They don't say, oh yeah, there's a fire. It's like, I can't stand this, I'm leaving. That's an alarm that's made from prime numbers. So natural patterns of oscillations are called normal modes. They normally occur. The rule for a string that is fixed at both ends, there must be a node at each end. So a normal mode has a distinct wavelength. That is, how much of a wavelength is that? Imagine, draw a wave. How much of a wavelength is this?
2 pi.
Well, think of it in terms of the fraction of a wavelength. How much is it?
Half a wave.
It's half a wavelength, isn't it? It went from the middle to the middle again. It's half a wavelength. How many pi would that be? Pi, yeah. What about this one? Goes from the middle, goes to the top, comes down again. That is one whole wavelength, which is 2 pi radians. This would be 1 1/2 wavelengths. This is 2 whole wavelengths. Yeah. This is 2 1/2 wavelengths. So there's a pattern here. And with a bit of practice you can pick them out. The wave speed is dependent on the tension of the string and the mass per unit length of the string, not the frequency. So the speed's constant. For each normal mode therefore each normal mode has a distinct frequency. These are multiples of the lowest frequencies, and they're called harmonics. So I want to go through this, and this is the skill I want you to get. So I would say for a guitar string, imagine the first harmonic. I'd like you to be able to draw that. I'd like you to be able to mark the node and the anti-node and the node. I'm going to give you a certain length. And I would say to you, oh, okay. So you would say to me, lambda in this case is equal to, L, the length in this case, is equal to lambda over 2. Half a wavelength. So that's the first skill. And then I'd say, oh, that's interesting. Let's say that the velocity is v. I'll give you a number. I'm just doing it with letters at the moment. Velocity of the energy on the string equals v. So then you'd say, oh, well, v is equal to f lambda. So f is equal to v over lambda. So for this guy, f is equal to v over, and what did we say? We said lambda is equal to 2L. Yeah? So lambda over 2L. Okay? Then let's take the next one. Node, antinode, node, antinode, node. L is equal to 2 lambda over 2. I'm being a bit cute there. I'm not calling it lambda, I'm calling it 2 lambda over 2. So lambda is equal to L. I've got this alarm bell going off in my head, so F is equal to V over lambda, so F is equal to V over L. Yeah, let's make it look the same. Let's say 2v over 2l. I'm going at the bottom. L is equal to 3 lambda over 2. So lambda is equal to 2 over 3l. F is equal to v over lambda. So F is equal to v over 3 over 2l. 2l, not 24, 2l. Can you see? Let me change colour pens to block this out for you. There's v over 2l, there's v over 2l, there's v over 2l. The first harmonic was 1 times that value. The second harmonic was 2 times that value. The third harmonic, or the third pattern, was 3 times that value. So if this was 50 hertz, what would this one down here be? 150. This is 1 times 50. This will be 2 times 50, which is 100 hertz. This is 3 times 50, which is 150 hertz. If this was 75 hertz, this would be 150 hertz, and this would be 225 hertz. So from the pattern, I can figure out, given velocity and length, I can figure out what the frequency would be. Just put numbers in, yeah? And I see for a guitar string, the second pattern is twice the frequency of the first pattern. Let's call that the second harmonic. Not because it's the second pattern, but because it's the twice the frequency. This third pattern is 3 times the frequency of the first harmonic. Let's call it the third harmonic, not because it's the third pattern, but because it's 3 times the frequency. So the 17th harmonic will be 17 times the pattern, the frequency of the first harmonic. So I don't know about you, but I don't need this stuff over here. I can figure it out. But the equations are there if you need them. Okay. Guitar string is fixed at both ends. It is 2 meters long. So a transverse wave has a speed, v, is equal to 5 meters per second. What is the wavelength of the first harmonic? So let's draw the first harmonic. I say lambda, I say L is equal to lambda over 2, so lambda is equal to 2L, which equals 2 times 2, which equals 4 meters.
Where's that?
What do you mean, where is that?
We don't have that page in our notes.
Oh, I'm sorry. Okay, I'm sorry. Then that means that, we'll see what the next page is like. It means that we got slightly different versions of it, so I'm sorry about that. Maybe on the video, as long as I'm recording, yes. And then what is the frequency of the first harmonic? Well, V is equal to F lambda, so V is equal to, so then therefore, which gives the F is equal to V over lambda, which equals V, which is 5, over lambda, which is 4, which equals 0.8 hertz. Well, that didn't work out. Let me do that again. V equals F lambda, F equals V over lambda. Oh yeah, my math didn't work out. 1.25 hertz. That's the scale. It might not be the first pattern. It might be, I might say, give me the third harmonic. I'm not going to ask you for the 19th harmonic. Be the first, second, third, maybe the fourth. But draw the pattern.
How will be the third?
So let's go through it. That would be the second pattern. That would be the third pattern. Yep. So a bit of practice on your patterns. You need it back up? Yeah. Okay. Have you got this page?
Yes.
I must have just slipped that thing in to make the stuff a bit more representative. I'm going to skip this because I want to. Let's talk about sound waves. Drawing these are going to be a pain, absolute pain. So we don't. What we do is we draw these. These are very abstract. They're not realistic. This, if you like, is doing the displacement versus position, or maybe it's doing the pressure versus position, you know, but it's an analogy, isn't it? It's saying there's no vibration allowed next to this wall, so that's like a node. There's a lot of vibration allowed near this bit. That's like an antinode. So it's using the analogy to draw the similar pattern. An organ pipe could be open at one end or open at both ends. A flute, for example, open at both ends. A recorder open at one end. Different allowed patterns. In this system, the tube that's opened at one end, there's a node at one end and an antinode at the other. In the tube that's open at both ends, there's an antinode at one end and an antinode at the other. Ironically, this is just like a guitar string. It's just the pattern is the opposite. Where you had a node, you had an antinode, etc. But it behaves just like a guitar string. It's not very interesting. You have your first harmonic, you have your second harmonic, you have your third harmonic. This is the interesting one, the one that's open at one end, because that is the first allowed pattern, and this is the second allowed pattern. Node, antinode, node, antinode. And the third allowed pattern would be you go like that, and you come like that, and then you go like that, and you go like that, and you come like that, and you go like that. And the way you can do it, if you like, is you go, there's your first pattern, and there's your second pattern, and there's your third pattern. Yeah? But the math is different. So let me... I can't what you're saying, sorry. Let's think about this first one. Let's do it up here. So L is equal to, how much of a lambda is this? It's going to be lambda over 4, isn't it? It's a quarter of a wavelength. So lambda is equal to 4L. And if I know that V is equal to F lambda, then F is equal to V over lambda, which equals V over 4L. Remember that, okay? If I look down here, L is equal to, how much of a wavelength is that?
Lambda.
It's not lambda, because you go from a middle to a you go, it's going to be 3 lambda over 4. So lambda is equal to 4 over 3L. V equals F lambda. F is equal to V over lambda, which equals V, and it goes 4L goes on the bottom and 3 goes on the top. If I look over here, this was 1 times V over 4L, and this is 3 times V over 4L. Whoa, 3 times the frequency, third harmonic. So a lovely conceptual question is, what is the second harmonic of a organ pipe that's open at one end and does not exist? Now, in fairness, I'm not going to talk about this in terms of, I'll use guitar strings, I'll use organ pipes that are open at both ends, or organ pipes that open at one end. I'm not going to talk in terms of, you don't have to remember that Oh yeah, a flute is like a pipe that's open at both ends. I'll keep that nomenclature simple so you know what model we're talking about. So, almost there, okay? So, an organ pipe is open at both ends. I'm not going to skip this one because it's just like the guitar string.
We don't have to know.
Then I'm going to skip it. I'll do it, what the heck. Okay, so organ pipe is open at both ends. The pipe is 5 meters long. And what is the wavelength of the second harmonic? Oh, I've got to do a bit of drawing here. That's going to be the first harmonic. And for these guys, it goes just in order of the patterns. So that's the second harmonic. Okay, so you've got to be able to draw these patterns. And for this one, I'm going to say L is equal to lambda, because it is, yeah? So lambda is equal to L. V equals F lambda. So F is equal to V over lambda, which equals, in this case, 330 over, which equals V over L. I missed that step out. Remember from there? So 300 over 5, which equals, sorry?
Oh, never mind.
Which equals whatever that works out to be, yeah? What does that work out to be? 66? 333 over 5? 66 hertz. So the frequency is going to be 66 hertz. And the wavelength, what is the wavelength? The wavelength is the same as L, which is 5 meters. Okay? Organ pipe is open at one end. The pipe is 6 meters long. Speed of sound is that. What is the wavelength of the third harmonic? So now I've got to remember, oh, that's the second pattern. L is equal to 3 over 4 lambda. So lambda is equal to 4L over 3. V equals F lambda. F is equal to V over lambda. F is equal to V over lambda is going to be 4L, and that's going to be a 3. Put my numbers in. 3 times 300 over 4 times L, and L is 6. So this is going to be 900 over 24, which equals 900 divided by 24 equals 37.5.
Yes.
And my wavelength, what is my wavelength? Lambda is equal to 4 times 6 over 3, which equals 8 meters. So it's that guy. That's the scale. Okay. Can an organ pipe that is open at both ends have a second harmonic? Open at both ends? What do you think? Yeah. Yes, it's the one that's opened at only one end that cannot. How much time do I have? I have 7 minutes. I can do this because I'm going to... yes, I can do this. So imagine that you have 2 tones, 2 frequencies, pure sounds that are slightly different. This is like what I've done here. There's one frequency, this is time. I'm doing a visual analog. This is another frequency. If you put them down like this, I don't think you can tell that they're different. If you overlap them, you can see, oh, look, there's this rhythm going on when they are in phase and when they are out of phase. And that is what happens with beats. There's the math. Basically, you have two slightly different frequencies, and you end up with this pattern. What we end up with is that the carrying frequency, the sound that you hear, is the average of the two frequencies. The hum, 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 the modulation of the sound. The beat frequency is a modulation of a hum. It gets loud and soft. That is the difference between the two frequencies. And the profile of the sound is given by that. I don't care so much about that. These are the two I really want you to get the idea of. So, a pure tone of 1260. And a pure tone of 1258. 1258 hertz. Sound together. What beat frequency? F beat is equal to the F1 minus F2. Just get me a positive number at the end. F beat is equal to 1260 minus 1258, which equals 2 hertz. What's the carrier frequency? F carrier. That's the sound that you hear. That's the hum pitch. Is the average 1260 plus 1258 over 2, which equals 1259 hertz. So the beat frequency is not a sound. It's the frequency of the modulation of a sound. And I'm going to stop there with that.